Hi, everybody. I hope your school closure coronavirus break is going well. I am coming to you with this video so that we can talk a little bit more about how to predict the products for reactions. This is just supposed to serve as an extra resource for you guys as you are working at home to get through the lab and get through some of the practice worksheets that I've given you. So we're basically just going to be talking about how to use this guide to chemical reactions, and then I'm going to go through some examples with you. So some of this we have already talked about in class, namely this part here, the thought process for identifying what type of chemical reaction has occurred. This is in order from easiest to identify with decomposition to hardest to identify synthesis. I don't think that we are having a hard time identifying these 5 types at this time, so I'm not going to spend a ton of time on this, but I just want to remind you that this section of your guide to chemical reactions is here, and you should use it to help you figure out what type of chemical reaction you have. But I'm basically just going to go through some example problems for you, starting with this one here. It says that zinc metal is added to hydrochloric acid and forms ... So if we have a problem like this, we're always going to start in the same place. We are going to start by determining the formulas for our reactants. So zinc metal is one of our reactants. Hydrochloric acid is another reactant. Zinc symbol is Zn, so I just write Zn. When I write the state of matter, it says it's a metal, which means solid. Metals are solid with the exception of mercury, which is a liquid. And it says zinc metal is added to, so plus hydrochloric acid. So this says acid. So the first thing I'm going to write is H1 plus. Then the hydrochloric bit, if it has that hydro beginning and that ic ending, what that means is that it came from an IDE ending. What that means is that it came from a non-metal on the periodic table. So the only non-metal that could possibly be is chlorine, right? That's where we get the chlor part of hydrochloric acid. And Cl will have a charge of 1 minus. So the formula for hydrochloric acid is simply HCl. There's 1 positive, 1 negative, so I don't need any subscripts to balance out this equation. Then, state of matter. All acids are aqueous. So you don't even have to do any thinking here. All acids are aqueous. And then we're going to form something. The question is obviously, what type of reaction have we formed here? Right? Do we have a decomposition reaction? No, because decomposition only has 1 reactant, and that is not what we have here. We have 2 reactants. We also do not have a combustion reaction because we don't have a hydrocarbon, we don't have oxygen. Single replacement, we're looking for a lone element plus an ionic compound or acid. If we flip back to our problem here, we see that we do have that lone element, zinc, and we have an acid. So this is single replacement. Once we have identified that we have a single replacement reaction, we go back to our guide to chemical reactions and flip to the portion on single replacement. With single replacement, we do have a couple of options. Right? We could have a metal replacement where the metal replaces the metal. So in this example, iron replaces copper. Right? Or we could have a non-metal replacement. The chlorine here replaces the iodine. Or we could have an acid, where so our metal will kick out the positive ion, the hydrogen in the acid. And this is exactly the situation we have here. Actually, if you look, the formulas are written here for us, but we're going to pretend that we didn't see this, and we're going to go back and prove that the zinc can knock out that hydrogen. Because remember, when we're talking about the single replacement reactions, we actually have to look at, is this zinc strong enough, and by strong enough, I mean reactive enough, is this zinc reactive enough to kick out this hydrogen? So we need to look at our activity series. So going back to the guide to chemical reactions, we need to look at the activity series. This is also on the back of your periodic table. We find zinc. So searching for zinc. Zinc is 9, and hydrogen down here is number 16. So zinc is higher on the list than hydrogen, which means zinc is more reactive, which means that the zinc will kick out the hydrogen in our reaction. So I feel totally comfortable writing hydrogen as the new lone element. Right? The zinc and the hydrogen essentially switch places. However, we do have to be careful. Hydrogen is one of the diatomic elements, so we do have to write H2. And then that hydrogen is a gas at room temperature. All right, once we have written the H2 here, now we need to go to the other part, the zinc and the chlorine. So zinc has a 2+ charge. And we know that chlorine has a 1- charge from up here. So we will need 2 chlorines to balance out our reaction. It's going to be ZnCl2 because I have to have 2 negatives from the chlorines to balance out the 2 positives from the zinc. Question is, what's the state of matter? Well, since we have an ionic compound, a metal with a nonmetal, and we started with an aqueous solution, we are still going to end with an aqueous solution. We did not evaporate the water, so we are still good here to put the aqueous symbol next to zinc chloride. Now we need to balance. So on the left side here, I have 1 zinc, I have 1 hydrogen, and I have 1 chlorine. On the right, I have 1 zinc, 2 hydrogens, and 2 chlorines. So the easiest way I see it, I see that the hydrogens and the chlorines are both unbalanced. So all I have to do is put a 2 on the left in front of this HCl term, bringing my total number of hydrogens and chlorines on the left to 2, and now I'm balanced. So that's the problem from start to finish, using the guide to chemical reactions, writing out the products, and balancing. Let's do another problem. So in this problem, I have ammonia gas reacting with hydrochloric acid to produce something. Again, our first step here is going to be to write the formulas for our reactants. Now, ammonia is one of those covalent compounds that we should have hypothetically remembered the formula for. But if you forgot, it's your lucky day. Ammonia gas is NH3. Of course, the state of matter is gas because it says it right there in the problem. So I have ammonia gas, and it's reacting with hydrochloric acid. I'm not going to go through the whole hydrochloric acid formula writing bit again. You can always rewind to that section of the video. HCl is that formula. And again, acids are aqueous. So I have my reactants. The question becomes, what type of reaction do I have here? Let's look back at the thought process for identifying what type of chemical reaction has occurred. I do not have a decomposition reaction because I have 2 reactants, right? I do not have a combustion reaction because I don't have a hydrocarbon and I'm not burning an oxygen. Single replacement, I'm looking for a lone element, but just as a refresher for you, I do not have a lone element here. Okay, so then we think to ourselves, maybe this could be double replacement. Well, with double replacement, we're looking for 2 soluble ionic compounds or acids. Now, I know that hydrochloric acid is obviously an acid, and therefore it falls under this category. However, NH3 is actually, let's see, non-metal and non-metal. This is a covalent compound. So NH3 prohibits this reaction from falling under the double replacement umbrella. Therefore, the only type of reaction left, if it's not decomp, combustion, single replacement, or double replacement, is synthesis. So that is the type of reaction that I have here. This is synthesis. So how do I deal with this synthesis situation? Well, I definitely need to scroll to that section of the guide to chemical reactions. Okay, synthesis. Oops. If I'm looking at my options here, I see combination of elements. That's not what I have. Non-metal oxide and water. I don't have any water. Metal oxide and water. Don't have any water. Okay, I could have a non-metal oxide and a metal oxide to produce an ionic compound, but I don't have any oxygens. So how do I go about solving this problem? Well, unfortunately, synthesis reactions are very challenging to predict the products for. If you find yourself in a situation where none of these match the reaction that you see, but you know that it's synthesis, then what I want you to do is email me, right? You will not be asked to predict the products of a synthesis reaction, right? This is just for practice. I'm just showing you how this works, okay? You will not have to predict this all on your own. However, I am going to walk through the rest of this problem here for you just so that you can get an idea of how to balance and everything. But I'm just going to tell you that the products of this reaction are NH4Cl. And just one product because this is synthesis, so I only have one product. And this is aqueous because I have an ionic compound. Then to balance, let's see. On the left, I have 1 nitrogen. I have 4 hydrogens, right? 3 from ammonia, 1 from hydrochloric acid, and I have 1 chlorine. If you look closely there on the right, it's the same thing. 1 nitrogen, 4 hydrogens, 1 chlorine. So this is already balanced. Woo! So we're done. Let's move on to the next problem. All right, in this problem, I have solutions of sodium phosphate and barium chloride, and they will combine to yield something. Again, first step, I'm just writing out the formulas for my reactants. So I have, well, let's give me some working space down here. Sodium is Na1+. It's in the first group on the periodic table. Phosphate is a polyatomic ion, PO4, 3-. So the formula for sodium phosphate would be Na3PO4. The state of matter is aqueous. In the problem, it says that we have solutions. All solutions are aqueous. These two terms are synonymous, meaning they mean the same thing. It's an aqueous solution. And so I've got sodium phosphate, it's aqueous, and I'm mixing it with barium chloride. Barium is Ba, which will have a 2+ charge. Chlorine is Cl, 1-. That's been discussed. So the formula for barium chloride is BaCl2. And it is also aqueous because, again, it is a solution. So what type of reaction do I have here? I'm not going to flip back to the guide to chemical reactions at this point in time because I feel like we can talk through it. It cannot be decomposition because I have 2 products, right? It cannot be combustion because I don't have any of the required reactants to have a combustion reaction. It cannot be single replacement because I have more than one, or I don't have any lone elements. And ultimately, you'll find that this is double replacement because I have 2 soluble ionic compounds. So this is double replacement. That looks like PR. This is double, there we go, double replacement. in a double replacement reaction, the two positive ions, so in this case, these two metals, switch places. So we'll have the sodium where the barium is and the barium where the sodium is. So what does that look like? Well, on the right-hand side, I'm going to switch and deal with the barium first. That barium still has a 2+ charge. The phosphate, PO4, still has a 3- charge. So I'm going to need 3 bariums and 2 phosphates to get them both to 6+ and 6- respectively. So my formula is Ba3 parentheses PO4 2. And we're going to come back to the state of matter. We have to discuss solubility rules for this type of problem. So like I said, we'll come back. Let's do the other product. I have the sodium now where the barium was. Hopefully you guys are familiar enough. NaCl. We know this is aqueous. This is salt, guys, salt water. Salt dissolves in water, so that's how we know this is going to be aqueous. So now let's look at state of matter for barium phosphate. Like I said, we need to go back to this guide to chemical reactions. Let's go to the very back page where it talks about the solubility rules. All right. Number 1, all alkali metal compounds are soluble in water. I already knew that, right? Sodium is an alkali metal, right? That's what makes this soluble. But over here, I'm looking for something about barium or something about phosphate. So let's just skip to that part. All right, looks like we have something about phosphates in the 4th rule here. It says all carbonates, phosphates, and chromates are insoluble, except those of the alkali metals. Now, is barium an alkali metal? No, barium is in group 2, which means this is not one of the exceptions, making barium phosphate insoluble. That's what this S designation means. Insoluble means that it fell out of solution, which is just a fancy term for saying we mixed 2 solutions together and we got a precipitate. Woo! That's what being insoluble means. So we formed a precipitate. Therefore, evidence of a chemical change, throwing it back to last semester. All right, we have a couple more here for us. Now we've got another example here. Let's just jump right in. It says iron 3 hydroxide decomposes into. So we've just got one reactant listed here. Go ahead and write out the formula for that. Iron is Fe. I have a charge of 3+. I know this because it has a Roman numeral 3. And that Roman numeral 3 dictates a 3+ charge on the iron. Then hydroxide is a polyatomic ion. Oh my gosh. I think I forgot to balance this last problem. Hold the phone. Let's go back. So sorry, guys. On the left over here, I have 3 sodiums and I have 1 phosphate. I also have 1 barium and 2 chlorines. On the right, don't have a ton of room here, I have 3 bariums, I have 2 phosphates, I have 1 sodium, and I have 1 chlorine. So maybe you're really quick and you can see what needs to happen already. What I'm seeing is a lot of 3s and 2s. So I'm going to try to get everything to that common factor of 6. Right? If I can get everything to 6, I think that'll work out the best for us. So I'm going to go ahead and start by try to balance these bariums. So I have 3 bariums on the right. On the left, I only have 1, so I'm going to go ahead and add a 3 here. All right, when I add a 3 in front of this BaCl2, it also impacts the number of chlorines, which now brings me to that nice 6 that I was talking about. So I'm going to bounce back to the right, put a 6 in front of NaCl, because that will give me 6 chlorines. And it will also give me 6 sodium. So now I'm going to bounce back to the left. I'm going to put a 2 here in front of the sodium phosphate, which gives me 6 sodiums. It also gives me 2 phosphates, which is exactly what I needed. I also noticed that I did not write a 3 here earlier, although I did already balance that. So now we're all balanced, guys. I'm so sorry about that. You know how I get. All right, if you have questions about balancing, see me, email me, do something. Let's go back to question 4 here. We were right in the middle of talking about the formula for iron 3 hydroxide. So there's a 3 plus charge on the iron. Hydroxide is OH1 minus. Make the formula for iron hydroxide Fe parentheses OH parentheses 3. Now, this is a solid, right? And in class, we talked about ionic compounds having high melting and boiling points. What that tells me is that it is unlikely that iron hydroxide or any ionic compound will be a liquid or a gas. Also, I don't have any water. There's nothing up here that says water. So that tells me I cannot have an aqueous solution, leaving the only potential state of matter as solid. And this is going to decompose. So hopefully you already figured out this is a decomposition reaction. All right, if we look at the guide to chemical reactions, what we'll see, most decomposition reactions happen with heat, right? We see the triangle above all of these reaction arrows. That tells us that we need to go back to our reaction and add a triangle here showing that we were heating up our solution or our solid. So how do we predict products for this reaction? Again, let's look at the guide to chemical reactions. I don't know why this isn't green, sorry. Looking at the guide to chemical reactions, we have B, a metal hydroxide. So what's going to happen is we're going to form a metal oxide and we're going to form water. So metal oxide and water. So if I go back to this, that metal oxide that I'm going to form is going to be between iron and oxygen. Now, iron from before has a 3 plus charge. Oxygen, we know, has a 2 minus charge. So the formula for this compound is going to be Fe2O3. And this is going to remain as a solid. Right? You might be inclined to change this to aqueous because it says that water is the other product. I urge you not to do this. In this case, we did heat up the substance. So this water is most likely a gas. All right. So we have predicted the products. Now we just need to balance. On the left, I am unable to keep the OH together. I'm going to have to separate it. So I've got Fe, I've got 1. In terms of oxygens, I have 3. This 3 distributes to both the oxygen and the hydrogen. So I have 3 oxygens and I have 3 hydrogens. On the right of my formula, on the right of my arrow, I have 2 irons. I have 4 oxygens, 3 from the Fe2O3 and 1 from the H2O. And then I have 2 hydrogens. So how in the world can we go about balancing this? Let's just start with something easy and manageable. I know that we have to put a 2 in front of FeOH3 in order to balance out my irons. When that happens, right, now this 2 is distributing to everything that I was distributing to before. So on the left, I now have 6 oxygens and 6 hydrogens. Let's look at these hydrogens first. We'll come back to the oxygen. I can make the hydrogen on the right a 6 simply by adding a 3 in front of H2O. Now, when I do that, I have 3 oxygens and 3 oxygens. 3 plus 3 is, of course, 6. So would you look at that? My equation is actually balanced. And that was much easier than we thought it was going to be. All right, guys, one more problem. Let's see. Ethane gas. So it says ethane gas burns in the air to form something. All right, first step, we write down the formulas. C2H6 is a gas. It burns in the air, which means it reacts with O2, which is a gas. Hopefully you see right away that this is a combustion reaction. I don't think that looks like English right there, but that's fine. That says combustion, right? And combustion reactions always have the same products, CO2 gas, right, and water vapor. So this H2O is going to be a gas. All right, so writing this reaction was super straightforward. Let's hope that balancing is as well. On the left, I have 2 carbons, 6 hydrogens, 2 oxygens. On the right, 1 carbon, 2 hydrogens, and 3 oxygens. So again, I'm going to encourage you to balance the carbon first, then the hydrogen, then the oxygen, all right? So I'm just going to get that out of the way so that's not in our way. Let's go about our business here. Let's balance the carbon first. I need 2 on the right, so I'm going to put a 2 in front of carbon dioxide here. What that does is, while changing carbon to a 2, it also changes my oxygen to a 5. I would have 4 from the CO2 and 1 from the water, which brings me up to 5. Now let's look at the hydrogens. On the left, I have 6. On the right, I have 2. I need to make the right a 6 by adding a 3 in front of the water term. So now my carbons and my hydrogens are balanced. I just need to evaluate how that last change changed my number of oxygens. All right, let's see. I've got 4 from the CO2, 3 from the water. That's not awesome, because now I'm left with 7. And there is simply no way for me to get 7 to equal, like I can't make O2 on the left here equal to 7. But I can find a common factor. My recommendation when you end up with this odd number of oxygens on the right is just to double the water term. All right, let's double the water term. So instead of making it 3 waters, let's go ahead and make it 6 waters. If we make it 6 waters, then now I have 12 hydrogens, and so far I have 6 plus 4, I have 10 oxygens. Go back to the left here and let's balance this hydrogen. I want to get it to 12, so I'm going to have to put a 2 in front of C2H6. When I add a 2 in front of C2H6, sure, it changes my hydrogen to a 12, but it also changes my carbon to a 4, which means I need to go back on the right and change my carbon here to a 4. Okay, so bear with me. I've officially addressed my carbons and hydrogens. I need to get back to the oxygens. I have 4 times 2, so that's 8. Then I have 6. 8 plus 6 equals 14. So I have 14 oxygens. To get 14 oxygens on the left, I would need to put a 7 in front of the O2. So it worked, guys. We just crushed that. If you were confused about how I got to this point, I would maybe go back to the balancing, to the beginning of when we started balancing this problem. Just watch the whole thing again. See if watching it a second time makes it a little bit better. Thank you guys for bearing with me on this super long video that I am making way past my bedtime right now. You guys can obviously see it's 9:11, so I'm 11 minutes late for bed. So I'm going to turn in was helpful. Please email me with questions that you continue to have. I hope you have a restful, safe, and healthy coronavirus break.